So till now, we have discussed about many concepts of operating system. In the previous lecture, we discussed about deadlocks or deadlock is handled. Now, till now, uh, we know about what are different components of operating system, how a process or thread is managed, how the resources are shared because of the concurrency or parallelism that is happening inside our hardware. So how we actually handle manage the multiple processes running at same time, and we also discussed about how resources are being shared when we have limited resources and there are a number of processes or threads which are running, and how they compete for those resources. And in case that and that a deadlock situation occurs, how we can resolve that situation. So we talk about prevention, avoidance, and detection algorithms. So in the last lecture, we discussed about detection algorithm and how we can basically avoid that and or recover our operating system from it. As I always say that each and every approach has a different pros and cons. So some approaches, some algorithms would be biased toward a particular type of data set or the problems, and while others differently handling the same problem. So no algorithm is complete in any sense. There would always be some accuracy attached to it and some performance parameter would be there. So it is never 100%. So now we are moving forward with a new chapter, which is about memory management. We will discuss chapter number 9 and 10 are focused on memory, how the memories are managed when we have so many processes running. Till now, we just know that the operating system uh, and allocates the jobs to the CPU or put it into the memory, and from the memory it competes for its execution onto CPU. CPU fetches those processes and then execute them and put into different states based on whether they are competing for a resource requirement or not, or otherwise the CPU executes it. So we know about that process. The missing component is how the memory is managed. As we know, our program is set of instructions, so those instructions needs to be uh, put onto the memory. The memory here, I am talking about a main memory. Now we discussed about different levels of memory. So we discussed about registers, cache memory, then RAM, then secondary storage, then tertiary storage. So all have a different level of speed, and they have different level of access speed, and also the closeness is different to the CPU. So more closer is the memory to the CPU, faster it is. And now we are going to talk about that particular subject, how this all would be handled, what are the concepts which give rise to multi-programming and help the multi-programming concept, because we know that if we have to put the number of the processes which are main in the RAM are basically giving us a more multi-programmed computer system. So how this is done, and we will discuss on that. So CPU fetches the instructions from the memory according to the value of the program counter. So inside CPU, we know that it is always looking for the next instruction to be fetched. It fetches the instruction, then operate onto that particular instruction. Now, we have seen high level languages. So you all worked on high level languages. In high level languages like Python, you write down the syntax in English like statement, then it is interpreted, converted into machine, and then it is given to the CPU for processing. So if I talk about one assembly instruction, so add a B, this is one instruction. So we have to perform sum. So whenever we write in Python a plus b, so it will be converted into this instruction. So here, this instruction has two parts. One is the opcode. This is opcode, and this part is operand. So it takes two operands. So how the process would work is the computer, the CPU would fetch this instruction from fetch the opcode. Once it fetches it, then it will fetch the operands. So fetch opcode, fetch instruction, decode opcode, fetch operand A, fetch operand B, and perform a plus b and store it in C. So this instruction is basically divided into this set of smaller instruction, and this is called instruction execution cycle. So this is a cycle how the instruction is executed in your CPU. So for putting and keeping all these things, CPU uses its local registers to hold the value, temporary value for the instruction, as well as for A, for B, and for C. So these values are held into the registers which are for CPU. So the instruction is decoded. It may cause operands to be fetched from memory. After the instruction has been executed on operand, the result would be stored back to the memory. Now, we are talking about memory here. So from where and which location the memory, the operands would be fetched, and then after the operation instruction is fully executed, where those values that would be stored. Now, what is this location memory? So we are going to talk about that today. So memory unit, basically, which converts these instructions A, or where it will be putting into the memory, is done by this mapping from C to the memory is done by a memory unit. The memory unit does not know what we are fetching and what process we are doing. It just sees a stream of memory addresses. So memory unit is a unit which is in between our CPU and as well as our main memory, which converts all the logical addresses into the physical addresses. We will talk about that. So we ignore how the program generates the memory addresses. We are not bothered about this particular part right now, but we are interested only the sequence of memory addresses. Those are generated by running a program. So whenever a program is executed, how it generates different addresses, and how we use those memory addresses to fetch the data from actual memory. So programs must be brought into from disk to the main memory and placed within the processes to be run. The main memory register are the only storage that CPU can access directly. So this is very important point, that CPU can access main memory and the registers. So the process of feeding from the storage is handled by operating system. So CPU has access of the registers as well as the main memory. So whenever, now another example here is a load R2, R0. So R0, here's the origin address, which would be found on R0. So this is an address. And here if we are storing, so R1 holds the destination address. So how that is computed and from where that comes in, that we are going to discuss. Most of the instructions, as we discussed, add, A, B, these are instructions which are given to our CPU. Those instructions, there are different type of instruction which require different type of machine cycles. So CPU clock, I'm not going into detail of this, what is CPU clock, because I hope that you understand it. What happens is a clock is running inside our hardware, and that clock is used to synchronize all the operations those are happening inside the hardware. Based on that, the clock speed is there. So you know that you might have a computer with the 2.3 gigahertz or 3.4 gigahertz. It is the speed of that clock. This clock says it can generate 3.4 gigacycles within one second. So this is the speed, and normally the excess CPU can do its work or execute one instruction within one cycle. So cycle is when one wave goes up and ends. Now this could be the simplistic, that within this cycle, so one up and down, our CPU executes one instruction. There are different types of instructions. Some take more than that, 2, 3, 4, and there are different cycles for it. So I'm not going to detail, but you could consider and resemble that there are instructions which require fewer CPU cycles. There are instructions which requires more CPU cycles to be to execute one instruction. So what does it mean? This means that CPU fetches the instruction, it has to decode the instruction. Once it decodes, now it knows that what operand it has to work on. There are instructions which are with single operand. There are instructions which are just without operands. So based on that, it will identify, once it decodes the instruction, it knows that operands to be worked on, then it fetches those operands. Now those operands would be fetched from the main memory, and if they are in the main memory, then it is good. Even then it will take some cycles. And if it is not in the main memory, then we have to fetch from the secondary memory, and that takes so much or so many cycles, and for that our CPU would be stalling. So this stall could happen, and that's why what is done is a cache memory is added inside or sits between main memory and CPU register. So as we discussed about cache memory, so it is basically intermediate and faster than RAM, but it is intermediate and sit between main memory and CPU register. So what happens? CPU uses the register to execute the instructions. If the instructions or data is not in the register, it will go to look into the cache memory, and if it is there, it will execute and fetch them and execute them. So because the cache memory is very fast, and then now we know that there are levels L1, L2, L3. So there are different levels. So those levels are attained to basically feed our CPU. So after L3, we will be hitting RAM memory. So in between our registers and the main memory, there are different levels of cache memory. Because it's fast, it's on board, and it can feed the CPU faster. That would actually decreases this stall time. So this stall time would actually get lowered, and this whole management of all the processes and programs are feeded to each level of memory is handled by memory management. So there are only finite number the values that can be kept inside those registers. Different types of registers are there, so they'll actually look into the cache memory whether to put at any other address. So where to put that, because your code is going to take the actual memory space. Now where to put that particular program inside RAM so that it can be accessed, because it requires a space to be for execution. So once the loader puts your program into RAM, it is actually binded into an actual address. So then it would have an actual address from where the instructions could be fetched. Your CPU would actually fetch those instructions sequentially from the program and act accordingly. So in today's lecture, we are going to discuss how this mapping of a program is done into RAM and how this whole management would be done here. So there are two views. One is a program view. Program view is I see my program as a contiguous memory space. Okay, just like an array. Array is your hard disk. Okay, so what we are going to do today is that I have a program and I have to put that program into RAM. Now, what location would be allocated to this program and how my program view, because I see my program is of 1 MB. I see this size only, but how this is actually placed into the RAM, that we are going to see today. Because there are number of programs, those are we talked about that concurrently we keep multiple processes into the memory. So if we have more number of processes into the memory, we say we have higher number of multi-programming. So multi-programming is higher. So my operating system can keep 1,000 number of processes into the same RAM as compared to other operating systems. So that is basically a benchmarking of multi-programming. So I try to keep multiple programs into main memory, but how that would be possible is one base approach is base and limit register. Now this is supported by hardware. So pair of base and limit register define the logical address. Or my program, let us suppose, is would be starting at a particular position this to a particular position of this. So this is my starting point, and the limit register I'm taking, the base is taken. So base is this, the R1, let us suppose 3300. Now my program is of different size, which is represented by this. My program size is this many bytes. So how it is handled inside memory is the base register would actually keep the location for the base value of the memory location. Okay, and the limit register would give me the size. So this is the memory block where my program would be residing. So this plus this plus this would make the end point of my the end size of my program inside main memory. So this is, let us suppose, RAM. This is the size of my program. Now rather than starting my program at 0000 location, because we have to keep multiple programs in the RAM, so it has to be different for each and every program. So for that, a base register is maintained. That base register would give me the start address. The start address would be added with the size of the program, which is handled by limit register to give me the total memory access block. So the memory from 30040 to 420939 is where my program is located into the RAM. So the base and limit register are used to keep our data set. Now another problem that we have different types of processes which are running. So if I have P1, P2, P3, and then there are some kernel program or operating programs, all are happening. So these are user program. So all these are running at same time, because we discussed that there are multiple programs running. So it may be possible how to, like, these can access the memories, so we have to preserve those location. Like this memory should be, if it is allocated to P1, should only be accessible by P1 only. It should not be accessible by anything else. So let us suppose this memory space is allocated to kernel. So this process should not be able to sneak into this particular memory, because all our memory locations, hardware is not distinguishing it. So we need a mechanism by which we can protect that the memory location of one process from another process. And particularly we are concerned about kernel level processes. When they are running and executing, they are also into the RAM memory. They are also into the main memory. Now how to protect? You can write a program which can sneak into the kernel and kernel memory location and change the content. That would corrupt your whole of the operating system. So here are operating system things working. So we need to preserve it, and how that is done, that comes under hardware address protection. The simplistic approach we have discussed, that is by base and limit register. So every time a logical address is created by your program, would be checked for base and limit register to find whether this is a legal access or not. We are going to discuss that. The operating system executing in kernel mode is given unrestricted access to both operating system and memory and user memory. So only the operating system could have access to each and every location, but not the user program. So what would happen? CPU would create an address. Now, what is this address? This is called a logical address. Now, when this would be created? When your CPU is running your program. Let us suppose it is running your program P1 and it started executing instruction 1. So it is at some location. So for user view or the developer view, your first instruction, let us suppose you declare I is equals to 0 is instruction 1. Okay, so it is at location 1. Now this is the logical address which is created by or generated by your CPU. So CPU would give me one logical address. Now I have to check for here, the translation would be done whether this is greater than or equal to the base or not. So based on this, the logical address, it would be converted into some mechanism into the memory. It has to be converted into the memory. How it is done? So first it will check this logical address would be the combination of base and the limit, and it would be checked for the base and limit whether it is within that particular location or not. So this diagram talks about how the hardware protection is provided. Let us suppose your CPU generates a logical address. I'll come to this also because this is a little complex than what I said here. So it will generate a logical address that would be checked for if it is greater than equal to base. If yes, then it would again be checked for whether it is between the base and the limit. If yes, the mapping is done. Okay. Now, if no, any of these are no, then a trap is generated. So if this address, which is generated for a program P1, tries to access a location which is outside the bound of this, then a trap is generated to the operating system for addressing error, and operating system can take measure to actually terminate that particular process because it is accessing a illegal memory location. So that could happen here. I'll come back to this logical addressing, how this is created here. What I discussed here, that is two things. Let me reiterate it. Is we have number of processes which are to be kept into the main memory. Then each process would have its own address, and for addressing we use base and limit registers. So the base would be telling us the starting point of that particular process, and the limit would be telling us how much size of the block is allocated to this process. This thing is clear. Now, second thing I talked about is the hardware protection. So because there are multiple type of processes those are running, so there needs to be some kind of protection so that one program should not able to access the other process memory location. So for that, the mechanism is here. So whatever address, the logical address created by by CPU, so it would be compared with the total address, which is whether it is valid or not. If this falls into the location, then it is a valid address. Otherwise, a trap would be generated which would terminate the process. So this is how the protection is captured. Now coming to the address binding, what I was talking about, how the address is there and how we keep that. So in address binding, programs are on disk and ready to brought into the memory to execute. So without any support, every program must be loaded to 000 location. Now, if we have multiple processes, we cannot keep multiple processes at same location, because every program is going to take the memory size. So each program, one program may be of 1 KB, which is a very large program. One may be of, with the data, it may be of 1 MB. So everything cannot be kept at same location, because it will override the data. So it is inconvenient. So how that is done, we talk about 3 addressing schemes right now. So addresses are represented in different way at different stages in the program life. Number 1, when we have a source code, the addresses are called symbolic. Now symbolic is the variable names, the constant names, instruction labels, such as variable count if you have declared. All these are symbolic addresses. So you create variables. What a variable inside a operating system? It's a location. So if I declare I is equal to 0, you worked on Python. So I is an address. So it's basically I is holding an address of a memory location where the value is 0. I hope you agree with me. This is symbolic address. So I is a symbolic address of some value 0. Actually, data is being held. So whenever we declare a data type, if you know that int I, if I declare int I, what does it mean? If I declare int I, what does it mean? It means that I is a pointer which points to a location which is of 4 bytes to hold a integer type of data. Okay, so when I talk about data type, it declares 2 things. One is a size, other is the operations those can be performed onto that particular memory segment. So inside memory, inside RAM, it is defining the size, how many contiguous memory locations are needed for this. Okay, and another thing I here is the pointer to that particular location. So it is holding an address. I holds address. Agree on it? Variables and the pointers are 2 things. Inside C, your pointers and non-pointer variables both are symbolic. Yes, so they are variables. So both are symbolic here. So what I'm talking about is we are not mentioning any actual address. We are not mentioning any RAM address. If I say the RAM address would be something like, I'm not mentioning like this. I'm mentioning a symbolic name for each and everything. Now these are representing, because in a program, we are working on a data. We are not working on a variable. Variables are used to represent some data which is stored inside your memory. So when you compile, when you execute a program, that variable is used to point to that particular location. When you write it, it is just a symbolic address for that. So there are symbolic addresses when you write up your program. When you compiled the code, compiled code addresses bind it to the relocatable addresses. Then it becomes a relocatable addresses. So let us suppose your instruction number 3, you have written which is 14 bytes from the beginning of this module. Okay, so then we have a relocatable addresses when you compile it. When you load it, when you load it into main memory, when you are trying to linker and loader we discussed. So when you load it, this would be converted into a absolute address. So what is absolute address? Is an actual memory address, which would be used to access the value. I hope I'm a bit clear here. How many of you are clear about absolute addressing and relative addressing? Is there any difference between two? Absolute would be the value and relative would be 14 bytes from the start. Okay, so this is relative addressing. So normally whenever we run a program, we do the relative, like we have written a program and then it searches for the header file. So it would be, we never give absolute address. It can search it in the relative addressing. It tries to first search in your what I say is a folder and then can go up. So similarly in your web designing, web development, you always give relative addressing. So whenever you program, you prefer relative addressing rather than absolute addressing, because that would be ported into any other computer also. So anyways, coming back, each binding maps one address space to another address space. So we are symbolic to relocatable, relocatable to absolute address. So this is how the address binding is done. Now, binding of the instructions and data to the memory. So how it is done? Three different ways are there available. One, at a compile time. So when we compile our program, then we can do that. But for that, what we need to know is the memory location already known to us. We know that the inside the RAM, this is what bunch it is allocated to my program. So something fixed is already there. So in that case, I can attach my program variables into the absolute address, which is called absolute code, can be generated and must be recompiled if the starting location change. So it is already allocated to us. If there is any change in the starting location, so if I say int, let us suppose I write down this. What is a here? Is it a pointer or no? And where it is pointing? If I declare int a10, what does it mean inside memory? Any answers? What a is holding? So a is this. A is pointing towards the first location. So a is this location. It's pointing to the start of the array. But rest is just indexing. If you do A1, it will point here, A2 here, A3 here, and so on. So this is a pointer. A is a pointer that points to the first location. Similarly, if the starting point changes, then we need to recompile our code. Okay. Then the second type is load time. The compiler generates a relocatable code. Now, relocatable code is relative code. Okay, if the memory location is not available at compile time, then the final binding is final binding changes till load time. We keep that till load time, and so the final binding is kept as is into relocatable code. Once the loading is done, this will be converted into an absolute address. So this is called load time addressing. Then we have execution time addressing. So the binding is delayed. We are not allocating anything till the time it is being run. Your process starts running and execution, and this execution time needs hardware support for addresses. For example, base and limit register, which I talked about. So the execution time binding will allow us flexibility because we can change the base register. The location of our program would change. If I see that there is another program already available at that base point, I can change the base location to some other place, and that would make loading and address binding more dynamic for running and executing the program. I need not to fix anything a priori, but I I can do that while the execution is done. And this is more dynamic way of binding the instructions to the actual memory inside the RAM. So this is the flow of your program. This we already discussed. You create a source program. This is compile time. When you compile it, some addressing are compile time addressing. Then you create object module, and other object modules are added. Now here is the load time when it is loaded, and then we have a execution time and run time. The binding here is during the execution time. Now remember this, we are going to talk about dynamically loaded system library. We are going to talk about this also, and this is called dynamic linking. Okay, so now there are two types of addresses. One is logical address, another is called physical address. Now the logical address is what I feel is relative address. I know that my program, what we discuss here is that the 14 byte from the beginning of the module, I'm looking for something which I know is from away from 14th byte from the beginning of that module. So this is a relative address. Now, one address is how the programmer sees it, how your or you're generated by your CPU. CPU generates some logical address, and one address is how it is actually stored onto the RAM. Now, both are different addresses. What is the advantage of it? Like the user program sees only its own addressing, its own addresses. Okay, so if you have declared a pointer, it is used as a pointer. It knows it has some location. Okay, it is just using that. Whereas there may be number of programs which are running at same time. They would be seeing the same pointer in the same way. But in actual, when we go to accessing the physical addressing, that would be the actual address which is maintained for RAM. So the concept of logical addressing space is bound to separate physical address, which is central to the memory management. We want to separate it to addressing schemes. I don't want to store the operating system don't want to store the data in a way your program is suggesting. I want to store it in a way that I feel more efficient of doing. So what we did, what operating system did is separating these two things. So one is what CPU sees the address which it is actually running, the address which is actually running, and the physical address is seen by the memory unit. I will come to it. This would also be clear as we are progressing. So logical and physical are same in compile time and load time, but logical or virtual. So if I say virtual address or logical address, both are same. So logical or virtual and physical addresses differ in the execution time addressing. Why? Because for compile time and load time, we know the absolute address. But in logical, the physical address would be different because program does not know where it would be. My program would be, given space on main memory. It just knows the base address and the limit address. So the logical address space is a set of logical addresses, whereas physical address space is a set of physical addresses generated by program corresponding to logical addresses. So this happens at RAM. So this space is the absolute address basically of the code. How that is happening here. So CPU generates the logical address. It is given to the memory management unit, which converts it into the physical address. So physical address is used to access and fetch information back and give it back to the CPU. So a hardware device, what is memory management unit? A hardware device that runs and maps the virtual address to the physical address. There are many methods, those are we are going to discuss, but the simplistic one is a relocation register, which is base and limit register. So here we start calling base register to our relocation register. That how the dynamic binding is done. Who is doing this conversion for from logical address to the physical address? So this unit is a hardware unit that performs the conversion and mapping. So user program deals with logical addresses and never sees the real physical addresses. So user program does not know where my actual instruction, where my A is stored. So it may not know it, because the physical address is different from the logical address. And this is done in execution time binding, and the actual access is done only when the reference is made. Without that, there is no conversion done. Whenever a reference is made by CPU, it generates a logical address. This conversion is done by memory management unit, and it goes to the physical address. So physical addresses are only created when they are needed. So logical address bounds to the physical addressing. So bound, we know the limit, bounds the logical address. So logical address would be limited by this particular. So we know that our program can require this much of the addressing scheme that we are going to discuss further also. Now let us suppose logical address. So in my program, I know my program ranges from 0 to max, and inside the physical memory, because we have a relocation register, so my inside memory, my address starts from R plus 0. So the first instruction, which is at 0th location, starts with R plus 0 to R plus 1 for the base value of R. So this is how the addressing is done. My program which is accessing 346th location in a symbolic way, okay, which is being mapped to 14,346 location on the memory. So who is doing this mapping is done by memory management unit. And why this is good? Because this memory management unit can put, there are different processes. This is, let us suppose, P1, P2, and P3. So there are different processes. For each process, each may be using 346, 346, 346 inside their code, but in actually they would be trying to fetch instructions from different absolute or physical address spaces. So this mapping is provided by MMU. So user program generates only logical addresses and thinks the process runs in the memory location from 0 to the max. So user program just thinks like that it is running into this address. However, the logical address must be mapped to the physical addresses before they are used. And concept of logical address space that bounds to the separate physical address is central to memory management unit. And this is where our memory management unit plays a bigger role. So dynamic relocation using relocation register. So we have discussed this because this gives us all the data of the processes be in the physical memory of the process to execute. Size of process that thus has been limited to the size of physical memory. So to obtain better space memory utilization, a dynamic loading is done. The routine is not loaded. So what is dynamic relocation? Because we know that if something is called, if something is needed, only then it has to be loaded. Now, if it has to be loaded, I know that if it is created and asked by the program, a new subroutine, I can give it a base register and the limit register, and that can actually use to point toward in the physical memory. So I need not to keep everything in the main memory. I can keep only those things which are required because of this relocation register. So let us suppose your main process P1 calls P2, P3, and so on. These are the functions. So which starts with P1. Whenever P2 is required, only at that point P2 would be called. And what we need here is just a relocation register to be allocated. So by looking at relocation register, which is allocated to P2, it can be kept into the memory wherever the space is, and then we can actually ask it to be loaded only when it is called. So main memory would be calling the routines whenever they are called from the secondary memory. So better memory and space utilization, and all routine kept on a disk in a relocatable load format. So it's already in a relocatable load format as we have discussed. So once they are loaded, they would be given some relocation register, the base address, as well as the limit, and that's how our program or the CPU would start fetching it. This would be very clear as we are progressing into the chapter, so don't worry about it. Okay, so now there are another concept, that is dynamic linking. Dynamic linking says that if we attach our libraries to a program, let us suppose you have so many header files in your program that if you link it, static linking is available, then you have to add all the code of those header files into your program. Okay, so to make it executable. So for that, the static linking works like, and it increases the size of your executable, because you have called 10 header files, your program size is 10 bytes, but your let us suppose 1000 bytes and 1 KB, and but you added so many libraries, it made it very large. And in that case, what can be done is, rather than this, dynamic linking can be performed. So if I go back here, so the dynamic linking is only loaded when it is needed. So a stub is provided inside the program for this dynamically loadable library. This would call this library, let us suppose you call libc. So normally all the user processes would call this libc file. Then this would be called whenever it is required. It would not be loaded. Now we know that we have a relocation register and limit register. We can assign a new location to this particular code whenever needed. And this is possible because we have execution time address binding. So because of that, we are able to load the libraries which are, you might, all those who are using Windows, they know that what is the meaning of DLL. So dynamically loadable libraries, those libraries would be loaded only when they are needed. So for that, the operating system checks if the routine is in the process's memory address. So this dynamically loadable also allows us to be shared, because if once it is loaded, it may be shared by different processes, number of processes, because we talked about that each user process location is protected. So let us suppose this is starting from 4000 till 45,000. So other process P2 cannot access this. But what if my DLL is here on a different location? So that is allowed. This can access, it has its own space here. So this is P2, this is P1, and this is DLL. So this relocation, dynamic loading, allows us this DLL to be used by this and this DLL to be used by P2 also. I hope that you understood how this would happen. Inside process P1 and P2, there would be a stub, code stub, which would call these libraries. Once these are called, these would be loaded into RAM, and then once they are loaded into RAM, we have relocatable register for this access for DLL. From there, we can actually find out, the CPU could actually find out what is to be loaded into the memory. Now, contiguous allocation. So whenever a program runs, okay, what is the difference between an array and a linked list? Do you see any advantage? This is, let us suppose this is an array, this is a linked list L. Is there any difference between two? This is contiguous. So this is, let us suppose this is a character type. So this is byte number 100. This is 101. This is 102. This is 103, 104. Where, so all these are contiguous. So this is a block of the memory which is allocated to the process. But if we have linked list, those are dynamically created, and we don't know whether if this is address number 0, it means this, it may be 200, it may be 400, it may be 500, and that's the flexibility. They are connected, but they are not contiguous. So the number one is contiguous allocation. Now there are problems related to it, so you will be able to actually identify what would be the problems. So main memory is one thing, whatever is the size. OS supports OS processes and user processes. So limited resources must allocate efficiently. Contiguous allocation is the only early method. So what was done? So let us suppose your program needs 1 kilobyte of memory. It will be allocated in a contiguous block. So from let us suppose 1000 to 2000 memory location. So just random. These are not actual. So just random. So this memory block is allocated to your program, and this is fixed. Okay, so main memory has two partitions. Now one, it keep the operating system part, and other are the user parts. So user processes are held in high memory, whereas the operating system processes are kept in lower memory. So each process contained in single contiguous section of the memory. Now we talk about memory protection. Again, it come again. Now, relocation register used to protect users' processes from each other and from changing operating system code data. So it also gives the operating system to change the code and data. So base register contains the smallest physical address. Limit register contains the range of the logical address. MMU perform the logical addressing dynamically and can allow a kernel being transit and kernel changing the size. So let me discuss. So relocation register. So this is the same thing we discussed previously. So relocation register scheme provides an effective way to allow the operating system to change the size dynamically. And here is what we have discussed. If the size is within the address, logical address, whatever is created is within the limit register, whatever is given to us, then it is good and allowed and converted into physical address. Otherwise, a trap is generated. So let us suppose it goes off for accessing 590 in place of 362, which is out of bound of this logical address scheme. Then it is basically, generating a trap here. And if not, it would be added to relocation register and convert into the physical address. So this is how they are done and protection is done. Now, multi-partition allocation. So there are number of processes, those are running. Let us suppose my RAM is of this size and it has 4 processes. One is operating system process, then allocate some memory, contiguous memory to process 5, then some memory is allocated to 8, then memory is allocated to 2. When process 8 executes, this memory would be freed, and this would create a hole in the memory. Let us suppose the next process comes, which is much smaller than 8. So some memory is allocated to process 9. This memory is now new hole, and now 10 processes added. This is new hole. So what is done? A variable partition size is allocated. We don't want our processes to be of same size. So whatever is the size of the program or the program which we are loaded into the memory can be variable, and based on its size, the amount of RAM would be allocated. So this would create holes. So hole is a chunk of memory which is available. Okay. As we move forward, let us suppose the process 5 goes away. Now this is a new hole here. Now we have two holes for 10, which would fit, and where the process 10 comes in, where it would fit, what memory is allocated to it, that is another algorithm. How to allocate and which hole is to be allocated to this process. This is basically managed by operating system, and it knows what are allocated partitions because it has relocation and limit, and what are free partition, what holes are available to be filled. So based on that, this computation is done, and we have algorithms for that. So the procedure is that one algorithm is first fit. As name says, whatever the first hole, because it has to be searched. Okay, so where is a hole? So it has to be searched. That information has to be searched. So for that, wherever the first hole that is big enough found would be allocated. So this is one algorithm. Then we have another algorithm, best fit. We try to find out the smallest hole that is big enough to fit process 10, but it must search the entire list unless ordered by size. It produces smallest leftover. Remember this thing, we are going to discuss this. So worst fit, allocate the largest hole which is available, must also search the entire list, produces largest leftover hole which may be more useful than smaller leftover hole. What this mean? So whenever the process 5 executes, it will create a hole, and this will be added into the available list of holes. So what would be done when P10 is coming? Let us suppose the size of P10 is smaller than size of P5. Now we have two holes available. Which one should be allocated? If we allocate the same thing, so P10 comes here, then there would be some memory space that would be unused because the size of P10 is smaller than P5. So there would be small size of memory which would not be allocated, and this would be a small hole. Okay, so this hole is also there. We may not get a program that could fit into this small hole because the size is, let us suppose, 10 byte of hole. So this may not be of useful. So similarly, what I was talking about, we try to find out the biggest hole for the first hole, whatever is found in first fit algorithm, then best fit would find out the smallest one, and the worst fit would actually give the largest one. So the best fit would actually allocate this location, but the worst fit would allocate this location to P10. So let us suppose here we are running the worst fit algorithm. So here you can see the hole size here is much smaller than the hole size here. This hole could be actually used to fit another process, but the hole created here cannot be used. So this is why there are different algorithms. Those are helpful for us, and everyone has a different advantage. If you know about defragmentation, now you can match it there. What does it mean? So defragmentation is you do that onto your hard disk rather than to the main memory. So put the holes together so that it could be used, and you can free more space and make it more usable to find out the smallest holes. Shifting your, basically what you're doing is you have so many data set, data 1, data 2, data 3, and within data 1 and data 2 you find the smallest hole. Within data 2 and data 3 you find biggest, smallest hole. So what we do is we order them. So this D1, D2, D2, D3 are put on one side of the hard disk, and all the small holes, they are put onto the other side of the disk, so that we can combine them together to create more free space. So now this is free space. I can use this more efficiently than whatever I wasn't able to do it here. So this is defragmentation, which is done in case if you can go to your control panel, then system storage, and then you can look at, there would be a button for defragmentation. You can see the fragments on your hard disk, and you can apply defragmentation there. So you can take time to look into it, but be conscious before you actually do that. Okay, so these holes create fragmentation. These holes create fragmentation. Now that fragment, the small holes, those are there, those are called external fragmentation. Now, because our hard disk is partitioned into small sections, and we may not be able to use it effectively, that is called external fragmentation. When there is enough total memory space to satisfy a request, but available spaces are not contiguous, and storage is fragmented to large number of small holes, then we say that external fragmentation has happened. We have the space empty, but the size of the holes is such small, we cannot store anything there, and that creates external fragmentation. And this problem is severe because all those small holes are useless and wastage of memory. So by a rule, the statistically analyzed that if we have n allocated blocks, then another 0.5 n blocks. So it means that the 1/3 of the total blocks n are lost into fragmentation, and this property is called 50% rule. So whenever we are loading our program into the main memory, then by 50% rule, 1/3 of the memory would waste into external fragmentation, and that's a big loss for us. Like if we have 8 gigs, how much is usable then? Only 1/3 is gone here. Okay, so based on that, you are using a smaller section of your memory for doing actual processing. So that is a big problem. Now, another problem is internal fragmentation. Now, rather than just going for a variable size partition, we can say we will give a fixed block of, let us 4 KB. Whenever a process would request something, we will give a block of 4 KB. So if it requires 10 KB of space, it will be allocated 3 blocks. So when the 10 is there, 4 would come here, 4 would come here, and 2 KB would come here. Now in that, the 2 KB here is free. So when this is free, this is called internal fragmentation. Let us suppose it just requires 2 bytes extra on top of 8 KB. Even then a third block is allocated, then the size of internal fragmentation is very high. So our allocation suffers from 2 types of fragmentations. One is external and other is internal fragmentation. There is external fragmentation. How this could be done is compaction. So what we do is, it's basically ordering your processes. So order them into one end so that the other end and holes come into other side, one side of the memory, and all processes goes on to the other side of the memory. Then we can actually manage our external fragmentation, because it will remove all those holes into other side, and it can be combined together, and we can utilize all. So the goal is to shuffle the memory content so that all places all free memory together to put that into the memory block. Compression is not always possible because if the relocation is static, then we cannot do it. If it is possible, this is only possible for dynamic loading. What an algorithm is doing. So it is allocating resources. When it is allocating those resources, it checks for the feasibility or the safe sequence. So if it is a safe sequence, you can put that process into the runnable formation. Then what would happen? Let me tell you what would be the sequence. Like, you keep on adding the requests. Let's suppose you have available resources. There are 5 processes. You already fixed. This is already fixed. There are 5 processes. Okay, based on your sample 5. So out of those processes, you will then start allocating the resources. Each process or thread or the customer would request for some resources. So as you keep on adding the resources, you will check for the safe sequence. If the sequence is safe, the safety algorithm would be executed. So certainly every one of you has to implement safety algorithm. So the safety algorithm would be running, and if it is safe, then you allocate those resources, and that would reduce the number of available resources. If the new request is coming and it is not a safe sequence, then you will not allocate and tell the user.